So a very quick finishing. So we have done most of the linear systems, and we have commented on indirect versus direct methods. So essentially, once I have a larger system, I need to switch to direct methods in order to minimize the round of error that is typically happening in Gaussian elimination. And one of the main, or one of the main methods that we mentioned here and that we programmed last time around is the Jacobi method. So in essence, this is very similar to fixed point iteration. I basically rewrite my equations so that I have vector x on one side and everything else on the other, and I can use that as a basis for iteration. Now in Jacobi's method, what we did when we did this method, one thing that we know that this method will succeed if I have a diagonally dominant matrix. Otherwise, it might succeed, it might not. I don't have a guarantee. So once I form this, once I actually write this up, I will get for each iteration, which I'm labeling as k, I get the next iterate by plugging things into this formula. So this is just a generalized formula that I can program, and we did so in class. And now all of the methods that we actually have, this is Jacobi method. The other two, Gauss Seidel and the successive over relaxation method, differ just in what is the information I use here for xj. So if I have iteration 0, and at iteration 0, I have four elements of that iteration here. I have x1, x2, x3, x4 at my initial guess. When forming this x1, which is my next iteration vector, okay, I use these formulas. If the x's here I use are all from that initial guess, okay, then I have a Jacobi method. However, and some of you actually made that mistake while doing the practice exam, if you actually use the most updated, so once I computed x1 for the next iteration, I have this new update for x1. If during computing x2, I'm actually using that update x1 that I already have newly computed, I'm a little greedy, okay? Then I will get Gauss Seidel method. Okay? And convergence will actually overall improve. So at each point, I'm using the newest version of this vector that I keep updating, so the newest elements that I have. Okay? So in that case, I essentially don't have to even remember. If you remember, we programmed this as sort of, we had x old and x new. So you're always using x new, whatever is the newest one you have. Okay? And that is essentially Gauss Seidel method. So this method will simply use for all of the previously computed ones. So if I'm computing x3 or x4, I'm going to use x1 and x2 that I already computed in the loop before. And that is Gauss Seidel method. And you can easily just redo the code that we had for Jacobi to do that. Okay? Now, what successive relaxation method says, okay, don't just use the entire new. Do a combination of both old and new. So this is just an attempt to improve convergence. You kind of play with this and you find for the system, and you know that you will be solving one system all over again. Okay? You kind of go to these three methods and you explore which one is going to give you the fastest result, and that's the one you use. So basically this relaxation will say, okay, don't just use, if I'm just using old version of this or the new. So I basically compute this with compute this iterate with the Jacobi method, and this one with the Gauss Seidel, and I basically scale things in between. So I take, for my lambda that is between 0 and 1, I scale my results. So I just actually do one more computation to get a little in between. So that sometimes improves convergence for doing this weighted mixture. And that's essentially it for the three versions. All of these methods are really similar. Knowing Jacobi iteration basically gets at the crux of it, and the rest are just variations. As you noticed in root finding, we also had like, what was it, 6 in the end of the methods, root finding methods? If we count in modified sequence, was it 6 of them?
Yes.
Yeah. So you all have all of these variations of methods because one method will not work great for all the problems I might have at hand. So I need a variation, or I need like sort of a selection of methods to work with in order to be successful. Okay? So essentially, for direct methods, we had Gaussian elimination, LU decomposition, which is a version of Gaussian elimination that is just trying to be smart in terms of how much time we are spending solving the system. And for iterative methods, we have Jacobi and then two variations of Jacobi, Gauss Seidel, and successive over relaxation. And in accuracy, we have a problem with direct methods that round off error, they occur and they pile up in large systems. So as I'm doing more and more calculations, I'm gonna over time pile up too much error. Okay. Now, the error that we are going to have in iterative methods, it's basically just a truncation error because I will always stop my iterations and I will not go further, and the actual round-off error is relatively small because I'm not doing all of this multiplication of one row, adding it to or subtracting it to the another, which is where basically most of the round-off error is happening. And in speed, I can really, this is so-called O of n3 problems. So if I have n by n equations, I'm doing some multiple times n cube operations. And operations are multiplication, addition, division. So each of those operations takes finite, however fast it might be. It still takes finite time on computer to do. So if you have an algorithm that is doing n cube of this, so if for n is 1,000, you're going to do 10 to the 9 of these operations on that order, maybe 2 times 10 to the 9. That's a lot. Okay? And that can really limit the size of the system you can actually solve. So basically, if I double the number of equations that I'm solving, if I go from 1,000 to 2,000, that's going to actually, the size difference is like 8 times, 2 to the 3 times. Even though I have just double difference in the size of the system, the time needed is 8 times. So of course, if I go for something 1,000 times larger, and n is million is not unheard of, it's actually very common. That's for a million, I'm going to increase my time. If I increase the size of the system 1,000 times, I'm going to increase time 10 to the 9 times, and that's a lot. Okay? So that's where LU decomposition helps some if you actually have a problem that is amenable to it. Whereas basically the iteration actually saves some of the time because I do have less of the computation. It depends on number of iterations. How fast are you approaching to the result that is close enough? And that's why we have this like successive or over relaxation and Gauss Seidel. Those were just like attempts to get to the solution a little faster and reduce the number of iterations. Okay. So it's usually faster than Gaussian elimination if I have a larger number of equations. And that's essentially it. You will actually see a note in your PowerPoint slides that the rest of the slides are advanced topic and we are skipping it for now. So they're essentially a system of nonlinear equations. Essentially, if I have now a number of nonlinear equations, I have to linearize each and then solve and try to find a way to solve them using linear systems. Okay? All right. So we are moving to a new topic, which is curve fitting. So this is our next to last topic. After this, we have ordinary differential equations, and we're essentially done. So curve fitting, basically, we will skip interpolation, and we will actually do ordinary differential equations. I used to teach that I did more integration, and then I would leave. Then I wouldn't have time for ordinary differential equations, and that's now changed. So this is suggesting reading. There are two chapters in the textbook that are relevant to this. Chapter 14 is so-called linear regression, which is the simplest way to actually do curve fitting. And the second the chapter after that, 15, is the generalized so-called linear least squares regression. Okay. So basically, just the base idea of curve fitting is that I have data. And when I have data, I want to say something about data. Okay? So I could plot it, but just plotting it doesn't necessarily tell me I need a number that tells me some sort of prediction where are things going. Okay? So for that, with like some sort of functional, I plot the data. I can plot speed versus time, or permeability versus time, or something is changing in time. Okay? And I can plot that, but in order to have a prediction, what's really useful to have, instead of just like a bunch of points, it's useful to have a functional relationship. I would like my permeability be a function of time. Let's say that I have drilling mud entering my formation, and drilling mud will damage the formation. I will really start clogging little pores of my, let's say that I'm injecting into a sandstone. Okay? And as I'm clogging those pores, in time, with more and more volume of this drilling mud injected, I'm going to change the permeability. I'm going to clog it up. Okay? So all I know is that my permeability goes down, but it'll be a little nicer to know how much does it go down. Okay? So for that, I would like some sort of functional relationship between either permeability in time, or maybe permeability in porosity. So as my porosity goes down, I know how permeability goes down. So those type of models are useful for prediction. Now, if I was this is just an example, plot of points. It doesn't necessarily mean anything, these points. But if I just do interpolation, so interpolation means, okay, take each and every one of these points seriously, and basically fit a curve that goes through all of those points. Okay. So for every 2 points, I can typically try, or every 3 in a row, I can try to fit a polynomial. So basically interpolation goes, I know that if I have 2 points, the simplest polynomial between them is a line. I know how to fit a line. Okay. So for 2 points, all I need to know is values of these points, and I can fit a line in between. Now, if I also try to constrain not just the value here, so I have this is x, this is f of x, right? If I'm trying to also constrain f prime of x, so a derivative, so I'm trying to fit both a value and a derivative at this point, then I actually get into polynomials of higher order. So I can start having like curved polynomials that are fitting not just a value of a function, but also its derivative. And that's basically how one gets this. Basically, I go patch by patch and try to fit these. Interpolation, in my opinion, in petroleum engineering, where data is super messy, is not all that useful. It's used, but not all that much. It is much more common to do a fit through the data that just tells me it's not necessarily passing through the points. It's trying to be very close to all of the points that I have, and we will define what does it mean to be close to. But as I'm passing through, I can see sort of like if I plot a line through this, I see a trend, I can see a slope. So with the next batch of data, I can see whether that slope changes. Okay? And that can tell me something about what's happening. So let's actually give some examples all petroleum engineering data that one would like to fit. One common one is that there's experimental data on capillary pressure and saturation. Is anybody in petrophysics yet, or is that next semester? I'll take that you're taking petrophysics sometime in the future. Okay, so in petrophysics, one of the most common measurements is capillary pressure curve. What does that mean? So initially I take a core, let's say that it's a sandstone core. I'm going to stick with the sandstone. Everybody did take sedimentary rocks, right? Some didn't. Okay, so sedimentary rocks are most common rocks we found in reservoirs. Okay, this is sedimentary rocks 101. Sedimentary rocks 102 is that you put a bunch of grains together, or rather, river or wind does it. So river brings a lot of grains, okay, into Gulf of Mexico, Mississippi River, right? As it keeps bringing that material, all of the grains that were there first, they're gonna start going down, and the new ones will keep getting deposited, right? So as they do, they kind of squish out the water that was there initially. As you're getting deposited, that water has to go out because you're getting squeezed. That water will, over time, leave cements that will bind those grains together. And as you cook and bake them at a high temperature and high pressure, you will end up with a stone that we call a sandstone. Okay. So this is a very crude way of describing what's happening. And that, of course, happens over geologic time. Okay. So that's how we get a sandstone. And some of the most common reservoirs, especially conventional reservoirs, are in sandstones. Okay. So let's say that I have a sandstone, and that's what is the most common rock in my reservoir. So I would actually like to know what will happen to oil as I inject water to flush it out. Right? So I want to know the pressures I need to do that, and I need to also know what will happen to that oil. Is there a chance of me disconnecting it? Because I would like that oil to just come out of the core as I'm pushing in water, which rarely happens if you're just pushing in water. So one of the basic experiments that is characterizing the rock that you will cover in petrophysics is capillary pressure saturation, which tells me, okay, I have initially water saturated core, and I start pushing in oil. So as I start pushing in oil, oil just doesn't go in there on its own, because water is typically wetting the sandstone rock. So water likes to be preferentially in that core. In order to push in oil, I have to apply pressure. As I increase the pressure difference between my oil and water phase, which is capillary pressure, it's that pressure difference between the two different phases, I start actually getting more and more oil in. And this tells me how much oil, so this is water saturation. As I'm pushing in the oil, this is oil saturation. So saturation is simply the fraction of the pore space occupied by a fluid of interest. Okay? So basically, as I'm pushing in more oil, my water saturation or fraction is decreasing, okay? And at some point, I actually find out that I cannot squeeze everything out. There's always a little bit of residual in there. Now, if I was to let water back in and reduce that pressure difference, that capillary pressure, I would actually go back, and I would probably go back this way, okay? So let me also point on the PowerPoint here. So if I was going here, up, 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 that's basically as I'm increasing capillary pressure between the two fluids, I'm also decreasing fraction of water in my rock. Now if I was doing this was so-called drainage. In imbibition, I would actually go back, and I would go back to this way, okay? It so happens that I would also have some residual in my rock, so I will never be able to push that oil back completely, okay? Now, either way, I might have just one experiment or two experiments. This is where I want to anchor my model to. So this, what's called here Van Genuchten model, is trying to fit a curve that I have a functional description to this data. Okay? It's not going in through perfectly here, but it's pretty close. Okay? Second example, and then once I have that curve as a functional relationship, it's really easy to type it into a reservoir, a larger reservoir model, and just have that. These curves are needed for modeling on larger reservoir scale. So if I was modeling my water flood on a larger scale, I need these capillary pressure saturation curves in order to model it. Okay? So somebody needs to tell me, and if I want to anchor it in data, I do it by curve fitting. Now, a second example is this similar example that I mentioned. Oh, I have permeability and porosity, and I would like a relationship or describe a relationship of the permeability, how much I can push through my rock versus how much pore space, or what is the fraction of the pore space I have. And this is, again, experimental data. You can see that it would extremely, if I was trying to pass through all of these points and trying to fit a curve that is passing through all of the points, it would be impossible. So it's essentially impossible to do this interpolation. I have to go to so-called curve fitting just to find the trend. And there was a model here that wasn't a linear model, so this was a model of a nonlinear function whose parameters were fit to be as close to all of these points as possible. And that's what we refer to as curve fitting. And now this functional model gives me a trend of permeability versus porosity. How is that useful? So this I did, for instance, for a bunch of core that came out from one reservoir. I might be drilling 100 meters over, okay? And I don't want to do all of this extensive study for that reservoir. In that reservoir, in order to predict what's happening, I'm going to use this functional relationship that I found by curve fitting. Okay? So in any modeling that reservoir engineers do to actually tell them how is a water flood going to come out, or is a water flood better method, or should I go with a polymer flood instead? Okay? I need these models. I need to model the rock in the reservoir, and this type of relationship is helpful in modeling the reservoir rocks. Okay? So this is basically motivation. Why would we like to curve fit? Now the simplest case, and this is where I'd like you to start actually paying attention to your sheets. Some of this you have on this plot is on the worksheet that I gave out. The simplest case says, okay, I'm going to fit a line, okay, to this data. Now the moment I fit a line through this data, so this data is really just a bunch of x and y's. So this point has x and y. Let's call it x1, y1. This point here is x2, y2. This point here is x3, y3, and so on. So I have n of them, whatever is the number of data. Okay. Now I would like to plot a line through this. So my line would have an expression that describes the line is y is equal to coefficient that I'm going to call A0 plus another coefficient that I'm going to call A1 times x. Okay? This would be a description of a line. Now, this line passing through here is modeling this point or this point or this point with certain error. Okay? So my line would tell me that for this x I'm going to get, or let me get a better example. So this line for this x value of x tells me that I should be here, but data is here. The difference between the two is the error. Okay? And what would I like this line to be? Well, I'd like this line to minimize cumulatively the errors between the line and all of these data points. Does that make sense? So this difference between whatever my data is and the actual description that a line would give for this data, I'd like that as small as possible. Now my problem is here is that all of these points, that I have a number of points, so I have to kind of minimize this in a smart way for every point. And what's typically done is that you will compute so-called sum of the squares of the distances. So each of these errors, okay, there's one error between my estimate and my actual data for each of these points. So I take those errors, some of them are positive, some of them are negative. Okay? I'm going to square them and sum them up, and I'm going to try to minimize. That's going to be the cumulative description of my error. Does that make sense?
Could you repeat again why we squared and not like take the absolute value?
Absolute value, that's actually going to come up in this worksheet.
Okay.
It's much easier if this is the objective of me minimizing, it's much easier to model this than anything else.
Just square it is easier.
Yeah. So essentially, criteria. So there are three possible criteria. Let me go one by one. So if I had just summed, okay, if I just had the error itself, sometimes this error is positive, sometimes it's negative. If I sum them up as is, that's a bad idea because they will cancel out. So I could actually have 2 points, and one is very large, let's say that it's 3, and the other one is -3. 3 minus 3 is 0, so cumulatively speaking, it looks like I don't have error. So it's a bad idea not to do anything to it. But his point is like, well, I could do absolute values, or I could do squares. Mathematically, squares are easier to analyze. So, second option is yes, I could have these, but there's this discrepancy in the absolute values, and it's not behaving mathematically when I'm analyzing this very well, and it doesn't always yield a unique fit. Also, I could also just do a maximum distance. Okay, so I could just take the maximum of all the errors and try to minimize that. So I just take, okay, what is the largest one? Let that largest one be the smallest. Okay. That's A, also mathematically hard to analyze. And B, then I'm giving sort of, there's this outlier. Let's say that I have an outlier point and all of the others are on a line. If I'm taking or trying to minimize the maximum, then I'm suddenly giving that outlier way too much credit. And I don't want to trust that one point that is possibly an outlier too much. So this sum kind of covers that up and looks at everybody a little bit. So those are the three options that we're gonna. Does anybody actually see that if I have a vector of errors, if you imagine this as a vector, all of these numbers is a vector of errors, this is essentially a square of the L2 norm of that vector. Okay. This would be the L1 norm of the vector of errors, and this would be L infinity or max norm of that vector. Anybody? Maybe? See that?
Could you explain the second chart again?
Hmm?
Could you explain the second chart again? Like what those two lines mean?
So basically, this line, so if I had these 4 points, okay, I could draw a line here that is basically this line is the same in terms of this is my error and this is my error,
right,
and their sum is what it is, right? And then if I draw for these 4 points, if I draw a line here, okay, I'm going to point so it's on the movie. If I draw a line here, again, the sum of the errors is the same. So both of these lines have the same sum of absolute errors. And this line is doing a great job with these 2 points, but awful with the other.
Okay.
And this line is doing a great job fitting these 2 points, but awful with this one.
Okay.
Whereas my square, if I use those squares, then I would actually go somewhere here. And that is lying in between all 4 of them, or is trying to take all contributions even. Okay? So also, in addition, its absolute values are kind of mathematically not so cute. Okay? All right. So now is basically we're going to go through the exercise on your worksheet. So pull out the worksheets. Okay? And I want you actually to simply, so there's this formula that I have that is sum for n points. Okay? And I want this whole worksheet is an exercise is saying, well, what is it in the case of just 2 points? Is that if I was trying to fit things to 2 points, okay, what would this problem look like? Okay? So first, in the first problem, I just simply want you to evaluate what SR is if I just have 2 points. N is equal to 2, so if you plug in N is equal to 2 to the formula that is on the top, what are you going to do? And the second point, and I want you to go through that variation, so that SR that you will get in point 1, it's a function, and assuming that you have data, x1, y1, and x2, y2, you have those 2 data points that you're trying to fit. This is SR, it's a function in A0 and A1, these mysterious coefficients that we are trying to find. Okay, so we are trying to find that fit. And I know something about functions, so this is, if I had just a function f that is as a value of x, f of x, what do I know when I have the minimum of that function? Let's say that I have a parabola. What is true at the very minimum? I have x, f of x, there's mathematical, this is calculus 1, whatever it is, that's the course 426, something like that. Derivative of f is 0. So derivative is 0 at the minimum, at a maximum, and an inflection point, right? So if we're looking at, this is a function of squares, so it's always a function, positive function, it can easily grow. Okay? So this is a function that is likely going to have a minimum. And that's why I like squares. Okay? So it's likely going to, so once I start analyzing and doing derivatives, I don't like absolute values when I'm doing derivatives, okay? So that's the mathematical reason. Okay? So if I have a bunch of squares, I can look at the derivative of this function, okay? And I can set it to 0 because I'm looking for the minimum. So that's what we're gonna do. Now, in the setting where my function SR is depending on A0 and A1, I have 2, I need to look at the partial derivative. We all know how to compute a partial derivative. I just freeze, if I'm looking at a partial derivative with respect to A0 on your sheets, you're going to freeze A1 and pretend that it's just a number, and you're going to do partial derivative, and then you're going to do partial derivative with respect to A1. So, get going, and if you need help. Yes, so whatever is, you're doing the partial derivative of whatever you did in 1. Okay? So solve 1 and 2. So this is essentially just pointing on the movie. We need to evaluate this expression for only 2 points. And then we have to calculate partial derivatives. Keep and save those worksheets because you'll have to turn them in on Friday when we go through all of this. Quiz. Right there. That's what you wrote is, okay, so now you can still use this.
We don't need to do that.
Just to kind of visualize that. And it's very low.
Yeah, I just wasn't sure, like, I didn't know if we were going to use it.
It's gonna actually make it easier to do partial derivatives. So then let's just
That's all I
And that's the one I'm working on.
How's this? Math 427J or whatever it's named. Is it this one? And then at the back we'll be setting this to 0. And she's getting a linear system. So
Wait, are we using the plus? Are we using the plus? Oh, this one, right? That's the question. Was that we can't just like fucking this one?
Maybe
The things with A is 0, right?
yeah, when you're doing partial derivative, you're treating everything as constant except that you're doing the partial
So only
derivative.
so you should only like, you don't need to multiply all.
Free is everybody else. But calculus is useful in engineering problems often, right? Therefore, regardless of how many points I have, I just have two partial derivatives. Yes, so I want for two points. So take SR from 1. And yeah, it's easier to, yeah. Everything is for 2 points. And the main concepts are there for 2 points. We don't need to go to N. Just to see what's going on. So just take the one that you computed SR, that one. So do a partial derivative of that. Yeah. Unless you feel like a challenge in writing sums, then go for it. Go for it.
Do I do that?
I mean, I just did the thing. The only terms that base with 0 matter, right? So you do this times this times this times this, and the same thing.
Oh,
And this is the fast way.
I think I did. He got the same thing then. So what we did was split it up into 2.
Yeah.
The derivative of a you bring down the
So this number 1 should be easy.
and then multiply
Just
that
make sure that you do have this in number 1. So now I'm taking partial derivative of that. Do we remember how to do partial derivatives? Is it still going on? Should I give you a couple of more? If you're bored, you can go to second page, feel free. So, for those of you who need a reminder, basically taking partial derivative of this is a composite function, so this is 2 times this, and then I find A0 this is the only guy depending on A0, so this is 2 times this entire function times minus 1. This is partial derivative with respect to A0 of this term. And the second one is 2 times this thing, again times minus 1. And the other ones I treat as constants. So now when I write that up, this is what I essentially have. Now for those of you who felt like a challenge and wanted to go for all of the n terms, you would really have a very similar situation. You would just keep going. You would just keep adding. Okay? N terms, not just 2, but n of them. So you would have actually a sum This is a sum from I is equal to 1 to 2, and in case of n, this would go to n of these points. So the difference between first term is that I have x1, y1, x2, y2. In the third term, if I had it, I would have x3, y3, and I would keep adding data. So adding more data doesn't add more insight for now, okay? The 2 points are enough. So is everybody clear on this partial derivative? Did you got something similar? We're getting there. And the second one is the same, it's just that now this is the term that has a1, and I'm doing a partial derivative with respect to a1. So basically I'm going to have 2 times this times minus a1, because this is minus x1, because that's the constant multiplying a1. So essentially we will have 2 times this term times minus x1. And in this second case, you're going to have minus x2. So I just cleaned that up a little with the minus going inside the brackets, and this is what I have. And I can again see a pattern. So this is my first data point, x1, y1. This is the second data point, x2, y2. So I can actually write that as a very simple sum like this. If I did have n points, this would not go to 2, but it would go to n, whatever that n is. I'm just going to wait for a second so everybody gets there, corrects it. Clear? Questions? You reminded yourself how to do partial derivatives? Calculus is useful. These are very practical engineering problems. Okay. Are we ready? So now I said that I wanted to minimize this SR, okay? So basically, in order, I know that at a minimum, the partial derivatives, just like first order derivative in a function of one variable would be, have to be 0. Okay? So I'm not just going to have one derivative 0, I'm going to have all of them for a function that depends on more variables. Okay, so the rule is really a generalization of that f prime of x has to be 0. So basically, both this and this has to be 0 for coefficients a0 and a1 that are minimizing this sum. So I'm still looking for them. I don't know them. But I know that at a minimum, I have to have that 0. So that's how I'm going to look for them. So basically, this equation equals 0, and this equation equals 0, both of them. So I have 2 equations in 2 unknowns. A0 and A1 are my unknowns. That's what I'm looking for. I'm looking for that linear fit through the data. Okay? So I have 2. What type of equations are these? Are they linear? Are they non-linear? Linear. So I have 2 linear equations in 2 unknowns. We know how to solve that, right? So we just need to basically, this is coming up with a linear system that is actually solving the problem. So that's basically what the exercise, we're not going to get, the bell is about to ring, but that's essentially what we will finish next time. We will set these 2 things to 0. And it's a simple 2 by 2 system. We know how to solve it in myriad ways. 2 by 2 is never a problem. Okay? And that solution will be a fit to our data. And we will be able to see easily how to generalize it for the case of n points that I'm fitting. All right? See you Friday.